In previous discussion, we have seen how do we use the Laplace transform to solve the initial value problem or boundary value problem. Okay, there is just a single differential equation. So now in this section, we will see how do we use the Laplace transform to solve a system. Okay, a system of differential equation. It is called a system when you have more than one differential equation. Okay, so in our syllabus, we will limit our discussion only to 2 by 2 system. Okay, it means your system consists of two differential equations, right? So first of all, let us take care of the notation. So before this, we have this notation, the Laplace of y t, okay, is the ys. Similarly, you have the Laplace of xt. Okay, so now it is going to be capital XS. Okay, and also you have before this the Laplace to the y prime is given by s ys minus y naught. Okay, so now if you have x prime t, then it's going to be as xs minus x naught, where the x naught and y naught are your initial conditions supposed to be given in the problem. Okay, now for discussion, let us consider this following simple system. So you have two equations here. The first one is dx dt equals to x plus y, or basically we can say that this is x prime equals to x plus y, given the condition for the x0 equals 1, and the second equation is y prime equals 3x plus 4y. Okay, and our aim is actually to get what is x and what is y. Okay, so by solving this, we are aiming for the equation for the x and what is the equation for the y. Okay, so all of the steps, the 4 steps that we have employed in solving the IVP and BVP before, okay, will be applied in this section as well. It's just that, okay, instead of employ it to a single equation, you are going to apply those steps to 2 equations. Okay, so you can expect the amount of work, okay, will be a bit longer for a system. All right, so we begin by applying the Laplace transform. So this is basically your first step. Okay, by applying the Laplace transform to both sides of each equation. Okay, so we just put the Laplace notation, okay, on both sides for each of the equation that we have. And then we replace the Laplace of x prime and Laplace of y prime here with these terms here. Okay, so by that we come out with this one. Okay, we put the initial condition given, which is -1 here, and the initial condition for the y is 0. So basically at this part here, it is 0. So we come up with this 2 equations here, which can be rearranged as this one. So basically, we just factor out the xs and this xs here. So put together the xs, so the coefficient of xs becomes s minus 2 then. Okay, minus ys equals 1. So that is your first equation. And from the second equation, you can see here, you can factor out the ys now. Okay, so on the left hand side, we have negative 3x plus s minus 4y equal to 0. Okay, which has the solution. So if we write xs as a main subject and ys as a main subject, we come out with this one. So the process to get this is actually just algebraic manipulation. Okay, so you substitute here and there to isolate the xs and ys. So basically, it's just the same way as you did in solving two simultaneous equation. Okay, so our aim, okay, at the first place is to get the xt and yt. So we know that we can get the xt if we take the inverse transform to these terms here. Similarly, we'll get the yt if we take the inverse Laplace to the ys here. So take the inverse to the right hand side term here. Okay, so you can see we have the denominator here in terms of bracket times bracket. Then we know this is partial fraction. So we do the partial fraction thing. Then we come up with this fractions here. Okay, similarly to the y, you you rewrite the term here in terms of partial fraction. Okay, and finally we take the inverse to the right hand side of these two equations to get the solution here. Okay, so those are the steps. So the process, the bulk of the work is actually here. Okay, when you from here to here. Okay, when you want to get the inverse transform. Okay, and in this example, reducing the system to xs and ys terms is just a process of algebraic manipulation. Okay, means the process here. How do you get from here to here is just manipulation. Okay, but somehow, okay, in certain case, the process could be a little bit of messy, okay, and you may get confused. Okay, so in the next example, we'll see how can we apply the Cramer's rule. Cramer's rule to systematically deduce xs and ys term. So I'll show you later, okay, in a while, how can we use the Cramer's rule, okay, so that we can get the xs and ys term here easily, okay, from these two equations. So we will apply the Cramer's rule to come up with the xs and the ys. Okay, so I hope you will still remember the Cramer's rule, or at least, okay, when I said Cramer's rule, it should have somehow rang the bell. Okay, because this is something that you have learned before in Engineering Maths 1, okay, SSCE 1693. Okay, but anyway, I'll just show you a quick view on the Cramer's rule before we go to the next discussion on the system, on solving the system of differential equation using the Laplace transform. Okay, this is Cramer's rule. Okay, so let's say we have a system of two linear equations and we want to solve for x and y. Okay, so you have this one, a1x plus b1y equals c1, a2x plus b2y equals c2. Okay, for example, you could have 2x plus y equals -1, and then 4x plus 3y equals 1. Okay, this is what you have before in 1693. It's just that before before this, the system that you have is more than 2 by 2 system. It's not 2 by 2 system. Okay, what you have before is 3 by 3 and 4 by 5, 4 by 4. Even, okay, could be up to 5 by 5 system. Okay, but this is just for illustration. So, and then by the Cramer's rule, the solution, okay, what we want to get from the system here is to know what are the values of x and y. Okay, so by the Cramer's rule, the solution is given by this one and this one. So x is given by, so first of all, this notation here, okay, is basically the determinant. Okay, so look at the denominator first. So this is basically the coefficient, okay, the coefficient of x and y. So we just take out the coefficient of x and y. Okay, so we put a1 and b1 and a2 and b2. Okay, so you can see in x and y, both of the denominators are the same. Okay, so and at the top here, so for the x, okay, in the first column, okay, you put the right hand side value here. Okay, first of all, you need to rearrange your equation so that all the variables should be on the left, okay, and terms without the variable should be at the right hand side. Okay, so C1 and C2 are basically constant. So for the x here, you put the first column here to be the value at the right hand side here. So you put a C1 and C2. So and for this one remains as B1 and B2. Okay, and then you compute the determinant at the top and determinant at the bottom. Okay, and do the division process, you get your x. Similarly for the y, the denominator basically the same. Okay, and for the y, you put the second column now with C1 and C2. Okay, so it means that for the first column, it remains as A1 and A2. Okay, so look here for illustration. So if we have the system here, then the value of x, then x is going to be, so put the denominator first. So it is the coefficient of x and y. So you have 2, 1, 4, and 3. And at the top, at the first column here, you put -1 and 1. Okay, the right hand side value of your system. And this one should be the coefficient of y. So this is 1 and 3. Okay, so at the top you have -3. Find the determinant at the top, -3 minus 1. Over at the bottom you have 6 minus 4. So this is -2. Okay, -4 divided by 2. And for the y, so you know the determinant should be the same. So the determinant should be 2 then. So you just take care of the numerator here. So you put -1 and 1 now at the second column. Okay, so it means that the first column, it should be the coefficient of x, which is 2 and 4. So now you have 2 plus 4 over 2. So this is now 3. Okay, so this is how we use the Cramer's rule to solve our system. It's just that in the Laplace transform, okay, the coefficient of x and y that we have here are not constants. Okay, it is not 2, 4, 1, and 3 here. Okay, they will be in terms of variables. Okay, but the process are basically the same. So instead of having a single value, -2 and 3 here, we are going to have expressions for x and y in terms of s. Okay, so I'll explain more on the Cramer's rule, okay, in the next example, okay, in solving the system using the Laplace transform.